We're going to take a look at our EMR unit assignment here, starting with question number 1. We did really well on question number 1. 100% of us, in fact, in both classes got this right. Accelerating charges produce. This is one of those best answer ones. They do produce electric fields. They do produce magnetic fields, but they produce, better answer is electromagnetic waves, because that takes into account the sinusoidal changing nature of the fields that are produced. Also the fact that it produces both of the waves at the same time and in phase with each other. So the answer is D. All of us got that right. Number 2, all of you also got that one right. We've got 5 types of electromagnetic radiation here. We want to rank them in terms of increasing wavelength. And we've got to be careful with that, but thankfully you guys were. Ranking them in terms of increasing wavelength is opposite of increasing frequency, and that's the way we have it memorized. My suggestion for a question like this is always to write down the order of increasing frequency. We've got radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Increasing wavelength, we're just going to read them backwards here. So when we look at the list here, starting from right to left, we would say gamma radiation is first. So that would mean the answer is either A or C. And then we would say that ultraviolet is next. That means the answer is got to be C. Regardless of what comes next, the answer has got to be C. Now, just go through it here. Visible light is next, sure enough. And then television, AM, radio. Well, those are both radio waves. Okay, as it turns out, television has a lower wavelength or a higher frequency than AM radio. You wouldn't have been expected to know that, but it works out. You just need to know that they're radio waves and that they're going to have a higher wavelength than all the other types. Which one is higher within the two doesn't really matter. The answer is C for that one, and as I say, 100% of you guys got that one right. Number 3. Lots of information here in number 3. Talks about ground penetrating radar. And then we have this graph of EMR that's reflected as a function of the wavelength of the EMR. The question asks us in number 3, the region of the EMR spectrum which the ground penetrating radar is classified. In order to determine what region of the spectrum the radar is classified is, we have to identify what the frequency of it is. Now, if we look up here, it tells us that the antenna has a length of 1 meter, and that's half the wavelength of the electromagnetic radiation. So we're going to say if the length of the antenna is 1 meter, then the wavelength is 2 meters, right? Twice the length of the antenna. Does that make sense? Now, if that's the wavelength, then the frequency would be V over that, 3 times 10 to the 8 divided by 2, which is 1.5 times 10 to the 8. Is that right? Yeah, 1.5 times 10 to the 8 hertz. Now, 1.5 times 10 to the 8 hertz is what type of EMR? Well, we didn't memorize that range, right, 10 to the 8, but we did memorize 10 to the 9 to 10 to the 12. 10 to the 9 to 10 to the 12 is, what is it? Microwaves. So 10 to the 8 has got to be radio waves. Means our answer here is going to be radio waves. Now, it's conceivable to answer this question without even going through that process. Ground penetrating radar. Radar is radio waves. Always. Radar is radio waves. That's what it is. So you could conceivably, if you had known that, answer that question and just by knowing that radar is a form of radio waves, just like TV and AM radio was a form of radio waves. Next question. Talks about this polarizing situation. We've got light going through a mineral, and it comes out of the mineral polarized. Really, what appears on the left-hand side is it's really all irrelevant. When it comes out of this mineral, it's polarized like this. The first two are polarized vertically, and then the third one is polarized at a bit of an angle like this, but almost vertical, right? If we have a polarizing filter that's oriented vertically like this, how much of this vertical wave makes it through? All of it. If we have a polarizing filter that's oriented horizontally, how much of it makes it through? None of it. And if we have a polarizing filter that's oriented like this, how much of it makes it through? The Y component of it would make it through, right? Does that make sense? the x component would not make it through. So some of it. How much of it? Well, we could do a vector analysis, I suppose, if we had angles in there. I'm pretty sure we wouldn't see that, but possible. We don't need to know how much of it makes it through. We just need to know that some of it makes it through. Now, we want to rank these in terms of the one that would produce the strongest signal to the one that would produce the weakest signal. 1 would be the strongest, then it would be 3, then it would be 2. Okay, all, some, and then none. So the answer for number 4 ends up being B, and 100% of you got that right. Numeric response number 1. If certain x-rays that have this frequency, what's the period? Well, the period is 1 over the frequency. We do the math there, 1 over 2.15, and we end up getting 4.65 times 10 to the minus 21 seconds. We just want the value of B, so we just fill it in as 4.65. Now, all of you got this right, but I will give you a word of caution with this. Sometimes we get a question where we're given the wavelength, and people like to try doing the same thing. Just flip it over to get the frequency. That's not what you do if you're given wavelength. If you're given the frequency and you want the period, you flip it over. If you're given the wavelength and you want the frequency, you don't just flip it over. Or if you're given the frequency, you want to find the wavelength, you don't just flip it over. Okay, if it's wavelength frequency, then you'd have to use this equation as opposed to this one. Number 5, 100%. The electric field component of the electromagnetic wave is this. Notice on the x-axis it's time, not distance. That means that the wavelength is not 0 to 4. Man, they should have had that as one of the options. Okay, you see, like, that's one complete wave, goes to 4. Okay, I'm sure that people would have picked this, 4 times 10 to the minus 6 meters. If it was electric field versus distance, then it would be 4 times 10 to the minus 6, right? That's not what it is. It's electric field versus time. So 4 times 10 to the minus 6 is significant, but it's significant as the period, the time for one cycle. And then if you want to find the wavelength, we're going to have to first find the frequency, 1 over the period. I think that's 2.5 times 10 to the 7? 5? What is it? 5? 2.5 times 10 to the 5 hertz. And then we're going to say lambda is equal to V over F, which is 3.00 times 10 to the 8 divided by 2.5 times 10 to the 5 gives us an answer of B, 1.2 times 10 to the 3 meters. 1,200 meters. It's a pretty big wavelength. What kind of EMR would that be, by the way? 1.2 times 10 to the 3 meters? I don't know. Let's look at frequency, because we memorize frequencies, not wavelengths, right? 2.5 times 10 to the 5, that would be radio waves, yeah. Okay, microwaves, 10 to the 9, 10 to the 12. This has got to be radio waves. And numeric response number 3 required us to use a protractor to measure some angles here. When we did that, we should have got an angle, this angle right here, as 39 degrees. And it should have been 39, not 38 or 40. Okay, you should have gotten 39 if you used your protractor properly. This one had to be, should have been 32 degrees. Now, because it did involve measurements, we do accept a bit of a range here, even though you really should have gotten those two numbers. The good news is, even though they tell us we have to be able to use a protractor on the exam, I'll have some protractors at the front of the room or at the back of the room in the exam, by the way, so you don't have to worry about bringing one. Unless you're comfortable with your protractor, then you can just use the protractors that I have. You know what, though? Even though they tell us we need to be prepared to use them, it's unlikely that you'll have to. What they've done the last couple of years when they've given us a question like this is they've kind of superimposed a protractor on the paper already, printed on the paper. So that eliminates the possibility of misaligning the protractor or setting it up wrong, right? They set it up for you. It's right there. You can't have it kind of off center just a little bit. The dot can't be off the dot. Like, it's got to work out for you, right? You just have to read the value off of the protractor that's superimposed there and then write it down. It's easier than the way we did this question. But we have to be prepared for the way we did this question just in case, even though it's not likely that we'll see it. All right, what do we want to find here? We want to find the index of refraction of the second medium. So we're going to say sine theta 1 over sine theta 2 equals n2 over n1. Sine 39 degrees over sine 32 degrees equals n2 over n1 is 1.33. So sine 39 divided by sine 32 times it by 1.33 should give us n2 of 1.58. I did accept what probably amounts to an overly generous range of this, anywhere between 1.53 and 1.63. So you could have been off by up to 0.05 for this and still get it marked correct. Next question, number 4. Critical angle between glass and air. We want to find a critical angle. We say sine theta 1 or sine theta c over sine 90 equals n2 over n1. Theta c becomes the inverse sine of n2, which this is going to be air out here, right? 1.00. Listen, we're not told the index of refraction of air. You're probably going to remember that, right? But if you don't remember it, where do you find it? If it's not in the question, it's on your data sheet, right? Now, there's only the one index of refraction on your data sheet. If you need anything besides air, it's going to have to be in the question somewhere. It's not here, so we look at our data sheet, we find it's 1.00. Over n1, which is 1.51. And when we do that calculation for theta c, we end up getting 41.5 degrees. Standard notation, we just record it like that, 41.5 degrees. 5, another numeric response, just keeps on coming. This one says, in an experiment similar to Young's double slit experiment, some students measure the distance between the first antinode and the fourth node. That is nasty. The first antinode, which is not the central, but rather the first antinode is this one. And the fourth node, we go from here to 1, 2, 3 here. That means n is equal to 2.5. How many people for this question said n is 2.5? Okay, how many people said n is 3.5? Okay, not from the central to the fourth node, it's from the first antinode to the fourth node. N is 2.5. The distance between those lines is 9 times 10 to the minus 3 meters. We want to go with meters here. L, the distance from the screen to the slits, is 3.0 meters. And the slits were separated, D, by 0.5 times 10 to the minus 3 meters. Right? 0.5 millimeters, or 0.5 times 10 to the minus 3. We want to find the frequency of the EMR. Before we do that, we're going to find the wavelength. Can we use that equation to find wavelength? Yeah, how come? Alex, how come? Yeah, L is way bigger than 10 times x, right? That's our rule of thumb. We multiply x by 10 and see if it's still smaller than L, and it is. We multiply that by 10, we get 9 times 10 to the minus 2, which is way smaller than 3 meters. So we're allowed to use this equation. We sub our numbers in here, 9 times 10 to the minus 3 times D, which is 0.5 times 10 to the minus 3, divided by N, 2.5, times L, which is 3. We do that, and we get, for the wavelength there, I don't know. I'm not sure what that works out to be because I don't have it written down. But it's not the final answer anyways. Once we get the wavelength, we want to find the frequency using V over lambda. If you had period, it's just flip it over, the inverse. 1 over the period gives me frequency. But wavelength, it's V over that wavelength. So 3 times 10 to the 8, regardless of what type of VMR it is, divided by that. And that finally gives me 50, should be 5014. 5.0 times 10 to the 14. What type of EMR is that, even though you're not asked? Visible light. Right smack in the middle there. A, B, C, D, we'd record that as 5014. And now we got this nice graphing question. We got a refraction problem, sine theta, Snell's law really, sine theta r versus sine theta I, or as we usually call it, sine theta 1, sine theta 2, and sine theta 1. You got this graph with a line of best fit already drawn. Sometimes you see the line of best fit drawn, sometimes you just see the data points, sometimes you see just the line of best fit. So there's 3 possibilities. Just data points, just line of best fit, or both, data points and line of best fit. Make sense? In this case, we have both. Okay, it doesn't really matter, but if we have both, at least we have a couple of options here. What I want to do first, when I'm analyzing this graph, is determine what the significance of the slope and y-intercept, if there is one, represent, what they represent. And I'm going to do that how? How do I start off to determine what the slope and the y-intercept mean? How do I always start off these problems? Y equals mx plus b, because it's a straight line. We know we're going to see one of these on our diploma exam, right? We know for sure. They tell us that we're going to see one. In all likelihood, a graph that you've never seen before. If you get lucky, it might be one of the ones we've done, but not likely. If it isn't one of the ones we've done, that's okay. You know how to deal with it. Always starts off y equals mx plus b if it's a straight line. The y-axis is sine theta r. I'm going to call it sine theta 2. M is the slope. The x-axis on this graph is sine theta 1. What about the y-intercept? Do I have to include that? No, because it looks like it goes through the origin, right? Okay, next we got to come up with an equation from somewhere else. What other equation do I want to write down here that has sine theta 2 and sine theta 1 in it? Brendan? Good. Sine theta 1 over sine theta 2 equals V1 over V2. Brendan, why did you pick V1 over V2 as opposed to, say, N2 over N1? Good. Since you're solving for speed, it makes sense to include the speed part of Snell's law equation. Now, let's rearrange this to solve for theta 2. Solve for sine theta 2, sorry. Sine theta 2 goes up by multiplying. V1 goes down by dividing. V2 goes up by multiplying. Becomes V2 over V1 equals V2 over V1 times sine theta 1. Does that make sense? You okay with the algebra there? Now what? Now what are we going to do with this? Cross off things that appear in both. Sine theta 2 appears in both. Sine theta 1 appears in both. Slope is equal to V2 over V1. Now we're going from air to this prism. We know the speed of light in air, V1, is 3.00 times 10 to the 8 meters per second. If we can get the slope, then we're good to go. We're looking to solve for V2 here. Easy if you can get the slope, because you already have the value of the speed of light in air. So how are we going to get the slope of this? How do we get the slope of this? Well, let's write this down actually over here so we can do some erasing here. You could pick 2 points on the line far apart. Never pick 2 points that are close together. Never. I don't care if it looks like they go perfectly through 2 intersecting lines or not. I don't care. Do not pick 2 points that are close together. Ever. Ever. If you're off by the tiniest little bit in one of those measurements, if you pick 2 points that are close together, then it's going to make your answer off by quite a lot. If you pick 2 points that are far apart on the line, then you can afford to be off by a tiny little bit in your measurement. So always pick 2 points that are far apart on the line if you're using the line. You got a couple of options here. You can use the line of best fit by picking 2 points far apart like this, or you can use the data points themselves in your calculator. Here's what I would suggest you do with either of those methods, the line or the data points. Open up your calculator. Everybody do this with me, okay? Open up your calculator. Go to the stat function. Stat. You've done this before, but only once or twice. You guys remember this? Doing this before? Stat function, edit. If you have anything in there, you probably do not, but if you do, just delete it. Now I'm using the line. I'm using the line of best fit here as opposed to my data points. Okay, if I'm using the line of best fit, then I want my coordinates for my first point and my last point. This would be 0.8 and 0.2, 0.4, 0.6, x and y. This one would be 0.94 and 0.66. So let's put those 2 points in my table here. 0.8 and 0.94 for my x values. And for my y values, I've got 0.6 and I've got 0.66. Does that make sense what I've done? Do not pick 2 data points and put them in like this. Pick 2 points on the line far apart and put them in like this. And then, once you've done that, click Stat again, go over to Calculate, Option 4, which is linear regression. If you're on a TI-83+, you're going to have to press Enter twice. If you're on an 84, you're going to have to press it 4 times. But you're going to get to the same thing, which is an equation y equals ax plus b, with a, the slope of this graph, being 0.42857. Does that make sense? Now, sorry, we got a typo there. This isn't 0.8 and 0.6. This is 0.08 and 0.06. So let's go back to our calculator and fix that. 0.08 and 0.06. Now let's do our stat calc option 4 again. Now we're getting a slope of 0.6977. We know that 0.6977, the slope, is equal to V2 over 3 times 10 to the 8 meters per second. And then we just solve for V2. And when I did that, I got, I think I got 2.08 times 10 to the 8, something like that. Which would express as 2088. We did accept a bit of a range here just because of your calculation of the slope, but it should be in that range, pretty close to that 2.08 times 10 to the 8. All right? Now, the second thing, I said if you're given the line of best fit, you can do exactly what we just did. If you're given the data points, only the data points, you've got to do something else. If you're given both the data points and the line of best fit, then I'd suggest you do what I just did. Right? Use the line. That's the easiest thing. Use the line. But if you're given only the data points, then what you've got to do is identify the coordinates of each data point, not just some of them, but all of them. Enter those into your table. So instead of entering 2 data points into your table, you'd enter 1, 2, 3, 4, 5, 6, 7 points into your table, and then just do the same thing with the determination of the slope. Okay? It should work out to be very, very close to the number that we just got, which means your answer Either way you do it will be within the acceptable range. If you have a line, though, it's easier to use just the line. If you have just the points, you got to enter them all. If you have both, then use the line. Okay? Does that make sense? Anybody calculate the slope by hand here? You can. That's fine. If you have the line, if you have just the data points, you don't want to go there. Okay? If you have the line, like, it may be just as quick to do it by hand, as long as you pick 2 points far apart, right? Like this and like this. Don't pick them close together. If you don't have a line, like you gotta use your calculator for that. You don't want to try drawing your own line of best fit, because then there's too many chances of making an error. It's too hard to get a perfect line of best fit. All right. Next one, number 6. Multiple choice number 6, which I think was a repeat question. I think we had this on a quiz or something before. We got a girl that's 122 centimeters high. That's her height, her object height. We'll call that HO. She's 40 centimeters in front of the object. That's DO. Her virtual image is upright and 54 centimeters high. HI is 54. We're looking for where she is, the image. We're looking for DI. We'll worry about what type of mirror it is in a second here. HI over HO equals negative DI over DO. Let's sub numbers in there. 54 over 122 equals negative DI over 40. 54 divided by 122 times it by 40 gives me a DI of negative 17.7 or negative 18 centimeters. So that means the answer has to be either A or C. Now, I don't like the terms convex and concave. I would much prefer the terms converging and diverging. Can you tell me what kind of what kind of mirror I have here? Converging or diverging? Forget about convex, concave. Converging or diverging? How do you know it's diverging? You can identify what kind of mirror you have here based on patterns in ray diagrams, or you can do another calculation. Without doing another calculation, how would you know it's diverging? You're right, by the way, but how would you know? No. Negative DI tells me it's a virtual image, and we're already told that it's a virtual image. No. With converging mirrors, there's one situation where you get a virtual image, right? When the object is really, really close to the mirror, we get a virtual image still. When you get a virtual image from a converging mirror, the image is bigger. And you might not remember that, and that's okay if you don't remember that, because there is another option. But if you remember that, so much the better, because it saves you from doing that other calculation. The image is bigger with a converging virtual image. Here we have an image that is less than half the height, so it is smaller. It is upright, virtual, and smaller. And the only time we get virtual, upright, and smaller is when we have a diverging lens or mirror. Diverging mirror is a convex mirror. Now, that's if you're drawing array diagrams or remembering the patterns. But there is another way to figure it out. If you don't want to do that, you can calculate the focal length. Now, I'm not going to do that here, but if I did, I would get negative something. The negative focal length would tell me that I have a diverging mirror, and therefore that it must be convex. Make sense? So either way, remember the patterns? Great. Or calculate the focal length. Either way, it tells me it's diverging. How many people did it patterns? How many people did it calculating the focal length? Okay, whatever. I mean, the only disadvantage to this is it's one more calculation, right? It's not a big deal. Whatever works for you. 4 observations, classical wave theory and quantum physics. What did we say yesterday? Classical wave theory is pre-Einstein. Quantum physics is post-Einstein. We often think of classical physics as wrong and quantum physics as right. Although we don't want to say necessarily 100% classical is wrong. Okay? In most contexts, it's not perfect, but we wouldn't say that as a blanket statement. But certainly, pre-Einstein, post-Einstein, usually wrong or right. Let's go through this now. We want to identify which 2 are classical, which 2 are quantum. Low intensity, in other words, dim light, the battery of your flashlight is dying, and you've got very faint light, very few photons. Few photons of EMR for a long period of time will cause the electrons to be ejected. Kathleen? That's classical. That's not right. It doesn't matter how long, how many photons you have. If it's not causing electrons to be ejected, it's not going to cause the electrons to be ejected, period. Okay, that was Hertz's explanation, classical theory, but it wasn't right. High-intensity EMR will not cause emission unless the frequency is greater than the threshold frequency. Is that right or wrong? So that's probably going to be quantum theory, right? And sure enough, it is post-Einstein. That is Einstein. The number of photons, or the intensity, has no bearing on emission of electrons. It's the frequency that has a bearing on it. 3, the energy of the emitted electrons will increase if the intensity is increased. So the energy of the electrons will increase if you have more photons. Does that happen? No. The energy of the electrons is not related to the number of photons you have. So that would be classical. The energy of the electrons is not related to the number of photons. The energy is not related to the number of photons. That's a correct statement. That would be quantum theory. So classical would be 1-3, quantum would be 2-4. Now these could be reversed, 3-1, and these could be reversed 4-2 as well, because it doesn't say to list them in order. Thanks. Number 8. Numeric response number 8 asks us to find the speed of light in a Millikan experiment. We know what to do there, right? 2 equations. We always write them down. The odds of you seeing this on your test tomorrow are, I would say, as close to 100% as you can possibly get. V is what we're looking for. The distance traveled is 35 kilometers times 2. Converted to meters is 70,000 meters. Don't know what little t is? Let's go over to the other side. The frequency was 500 hertz, giving me a period of 0.002 seconds. To find little t, we'll divide by 8. I believe that's 1.25. What does that work out to be? What is it? 2.5? Okay. 2.5 times 10 to the minus 4, which we sub in here for little t, the time for 1/8 of a rotation. Solve for speed. And it works out to be 2.80 times 10 to the 8 meters per second, which we're going to record for that speed as 2808. 2.80 times 10 to the 8 meters per second. This, I think, is a great question. We've got a diffraction grating here that, when we're using green light, that produces this interference pattern. Bright spot, we've got another bright spot over here at 13 centimeters, and another one over here. But now we're doing a couple of things to it. We're changing it around a little bit. We replace the green with red. So let's say we replace it with red. What happens? Well, we still get a central maximum. We still get a first order maximum and a second order maximum. But where would they be? No. They would be further away. Now, how much further away? I'm not sure exactly. But they would be further away because although red light, if you look over here at the picture on the board, or on the bulletin board, on my 137th favorite band of all time, red light refracts the least, red light diffracts the most. So red light will be further away from the central maximum than green will. Now, we switch it back to green. Switching it back to green. But this time, in trial 2, we're making the lines closer together. That means little d goes, if the openings are closer together, little d is bigger or smaller? Smaller. Little d is smaller. Now, if we look at our equation that describes this, if little d goes down, then x, which is the distance between two maxima, must go up, right? If you look at this, if we rearrange it to solve for x, lambda times n times L over d, if d goes down, x must go up. That means that the green, we don't know exactly where it's going to be, but we know it's going to be further away than the original green was. So let's look at our question now. The row that contains the observations that are expected for trial 1 and trial 2. Trial 1, we know red has to be, I don't know what it is, but it's bigger than 13. So that means the answer has to be either A or B, because that first red maximum is bigger than 13. For trial 2, we know that green also has to be bigger than 13. How much bigger? Not sure. If we look at trial 2 here, or B, sorry, then we can see that that green is bigger than 13 centimeters. So the answer for this one is B. Number 8, 4 different wavelengths. We got a work function of platinum, and we want to know which wavelengths would cause a satellite with platinum to become positively charged. In other words, to lose electrons to become positively charged. Here's what I did. I said, here's the work function. W is equal to hc over lambda max, and I solve for lambda max. So let's find lambda max here. Because I've got my work function in joules, I'm going to use 6.63 times 10 to the minus 34 joules seconds times 3 times 10 to the 8 meters per second, divided by the work function that's given to us as 8.5 times 10 to the minus 19 joules. We get a threshold wavelength, maximum wavelength of 2.34 times 10 to the minus 7. So you guys know that if this is maximum wavelength, you got to be below that wavelength to cause the electrons to be ejected. Above the threshold frequency, below the threshold max. So we want to be, what, 1 and 2? Because they're the only ones that are below the threshold wavelength. Does that make sense? The other ones are above the threshold wavelength. They'd be below the threshold frequency. So 1 and 2 is our answer there. Or C is our answer there. Number 9. EMR is incident on a cathode. Photoelectric effect is observed. The electrons are ejected. Which of the following graph represents the relationship between maximum kinetic energy and intensity? What's intensity mean again? The number of photons. So how is the kinetic energy related to the number of photons? Alex? It isn't related. It isn't related. So that means the answer for this has got to be A. This is the only one that shows no relationship. Right? All the other ones show increased number of photons. Something happens. A doesn't. Number of photons doesn't change the kinetic energy. So the answer is A. We're going to come back to this one just because of a time thing. I think we'll have time to do it, but we'll come back to it just in case here. Number 11, we want to find the wavelength of this satellite. Wavelength is V over F, which is 3 times 10 to the 8 divided by 1575.42 times 10 to the 6. because we got to be in hertz. We solve for the wavelength here. Number 11 works out to be B, 0.190 meters. The time taken for a signal to travel that far, well, we're going to use just V equals D over T for this. The time taken is D over V, which is 20,200 times 10 to the 3 meters, divided by 3 times 10 to the 8 meters per second. And that one works out to be, is that number 9? 6.73 times 10 to the 2. 6.73 times 10 to the negative 2. We told you to skip numeric response or multiple choice 12 and numeric response 10. We'll go to multiple choice number 13 here now. Here's the equation that we saw yesterday for the first time. We said if I was going to derive that, which I can't even derive that because it's too hard. We don't have to be able to derive it, so I'm not going to worry about it. But if I was to derive it, I would derive it from the law of conservation of energy and the law of conservation of momentum. Just because I can't derive it doesn't mean I don't know where it comes from. I know that I would use those two laws to derive it. I just haven't been able to derive it. We had 2 more questions. We missed numeric response number 2, was it? And then that big collision question that we saw earlier on. Let's go to multiple choice numeric response number 2. Oh, we missed this one? Oh, how did we miss that one? Yeah, that's a great question. Okay, this is the one with like 9 possibilities, 8 possibilities. So here's the situation. We're told here that we've got an optical apparatus. We produce a focused real image. If we produce a focused real image, then that means we've got to use a screen, right? Because that's how you see a focused real image is on a screen. Now, where we put the screen, we're not sure, but we know we're going to have to use a screen. We also know we're going to have to use some source, and it doesn't really matter which source you use, a laser or a candle. I suspect that most people put a candle because that's what we used in our lab, but it doesn't really matter. A laser would work as well. It's just harder to determine that it's focused in a candle, or sorry, in a laser, that's all. Candle is easier to determine when it's focused. But number 1 or 0 would work there. Now, if we're producing a focused real image, we know we cannot use this because this just produces a virtual image. This just produces virtual. This just produces virtual. And then a diffraction grating or a double slit apparatus, like it just doesn't seem like it fits, right? Focused real image, focal length of 10 centimeters. Like we're talking about a lens or a mirror. So that means it's 0 or 1 work somewhere, 9 works somewhere, and then it's either 2 or 4 that work somewhere. Let's guess. Let's say our object is placed right here. Let's say our converging lens is placed right there. And let's say our screen is placed right there. This is 15 centimeters from 5 to 20. This is 15 centimeters from 20 to 35. Does that work out? Well, let's try it. 1 over F is equal to 1 over DO plus 1 over DI. We're told the focal length is 10. DO here in this case is 15. We solve for DI there, and it works out to be 30. Is that DI 30? That DI is, no. That DI is 15. We measure it from the optical apparatus, right? So that means that this isn't going to work at all, is it? Doesn't matter where we put it. Like that's the only place we could put it and get a real image formed. And that doesn't work because the distances don't work, right? In order to put it right here, we got to get an image distance of 30 centimeters. In other words, I'd have to put my screen over here somewhere, not 15 centimeters away from the lens. So we know it's going to be device number 4. So it's 0 and 4 and 9 or it's 1 and 4 and 9, but where are we putting them? Let's try putting the object, whether it's the laser or the source right there. Let's try putting the, well, I couldn't put the mirror right there, could I? And the screen right there, because you're not going to get a real image on the other side. So let's try it this way. 15, 15. 1 over f is equal to 1 over do plus 1 over di. 1 over 10 is equal to 1 over, the object distance would be 30 here, right? From the object to the mirror is 30. di works out to be 15 if you do the math there. Is di 15 the way that I have it drawn? Sure enough, that works. So we could say 0, 9, 4, or we could say 1, 9, 4. We could also reverse this, flip everything around, and go 4, 9, 0, 4, 9, 1. Right? Now, what else could we do? I missed this one, but somebody in the last class spotted this one. We could also set it up like this. We could also have the mirror here. We could have the object here, and we could have the screen over here. 15, 15. Our focal length is still 10. 1 over 10. Our object distance here would be 15. Our image distance would be, do the calculation, 30. Is the image distance 30 there? Yeah, so that works as well. We could say 9, 0, 409. Yeah, 409. 419 or 904, 914. So those are our 8 possibilities, the 4 we just got and then the 4 we erased a minute ago. Yep. Yeah, that's exactly what I'm doing there, right, between these two and these two, right? So we go 4, 0, 9. We could have it exactly the opposite and go 4, 0, 9 that way, which ends up being 904. And finally, our last question. We did have time to do it. That's good. Wherever it is. We'll find it. There it is. Here we wanted to find the momentum of the electron after this collision. This is a great question. This is a great cross-unit question. It goes back to what we learned yesterday, but also goes back to Unit 1, conservation of momentum in 2 dimensions. Let's label this. We have a photon here that has a momentum. We'll call it object number 1. The photon has a momentum of 1.83 times 10 to the negative 23. Object number 2 is at rest, 0 momentum. Object number 1 goes up this way afterwards, and afterwards it has a momentum of 1.72 times 10 to the negative 23 Newton seconds, 85 degrees, and we want to find the momentum of object 2. We got a funny angle. We take it off to the side. This is x, this is y, this is 85 degrees. Let's solve for x. 1.72 cosine 85 degrees. 1.72 times 10 to the negative 23 times cosine 85 gives me an x component there of 1.499 times 10 to the minus 24. The y component is 1.71345 times 10 to the minus 23, using the sine function there. Let's block that off. Now let's do our x components and y components like we did back in Unit 1. Usually we'd say m1 v1i plus m2 v2i equals m1 v1f plus m2 v2f, because we have two objects. But remember that this object, this first object, is not mv, it would be h over lambda. Remember yesterday? The momentum of a photon is h over lambda. And this one would be h over lambda as well, because it's a photon. But the good news is, it doesn't really matter what the equation is, m times v or h over lambda, right, Austin? We know the value of it, right? The value of the first one is 1.83 times 10 to the negative 23. This is 0 because it's at rest. This is, we just found it, 1.499 times 10 to the minus 24 plus P2F. Solve for P2F. I don't know what it works out to be. It doesn't really matter. Then we do the same thing for the y component. But for the y component, the initial momentum is 0, because it's all on the x-axis. The final momentum is 1.71. Plus P2F. Solve for P2F. And then we just combine them. Anybody see a shortcut there? There is a little bit of a shortcut there. If we solve for either x or y, let's say we solve for x. If we have that value and we already know this value of 45 degrees, then all we got to do is say cosine 45 is equal to x over the hypotenuse. So we can avoid doing one of the components if we want to. It doesn't save much work, but it saves a little bit.